Okay, one of our colleagues asked me in an email about this problem here. And let's see, I'm using my tablet here. Let's see. All right. That's funny. I'll use purple. Where's black? How about dark gray? Anyways, which there's a couple of things going on. I don't remember exactly, but I know one question was at position 1, I guess it was, which one of these represents the best one, and it would be AH for the A vector. But let's go over it. So let's say we're at position 1, and so we know that there's a tension here from the whatever this is, a bar or rope, and then there's a weight vector. So these are the real forces, and there could be an F centripetal. And this is very similar to, remember, A centripetal equals V squared over R. So F centripetal equals mv squared over R, which is ma. It's Newton's second law. I mean, we could do this in accelerations, but we could say acceleration of gravity is down, acceleration of t. So what happens is now we can see that, let's see, we want to put this into the F centripetal, and the T are obviously equal and opposite, and this F centripetal is not constant because there's going to be, this is the place where it turns around, then V could be 0. And so there's no centripetal force. But we have W, the weight, can be broken up into components. And so we would say that we've got the tension, we've got the F centripetal, and we know the path is the dotted line, so this is going to be a W perpendicular to the path. So there's going to be some component of the weight this way and some component of the weight that way. Oh, excuse me, that would be, yeah. And this is the perpendicular, this is the parallel, because we've got, and that's a tangent. So weight and weight. So you see how, because the string is rigid, or if it's a rod, the only thing we have left is the tangential component of the weight, which is here. And that means that at point 3, that would be H. That's the best one anyway. Now, notice here, one thing you may not realize, but this is where V is at a max. So this is at point 1. At point 2, we've got T, and we've got W, and we have also the centripetal force. And now there's no components, but notice there's no, all the components are perpendicular to the path. So at point 2, A equals 0, because there's no net force. But also notice then, this is why if you're on a swing, You may notice that sometimes when you're at the bottom of the swing, it's a terrible picture, and it's because I'm a terrible artist. So if we look from the front and we see the swings, we might notice at the bottom that this thing could sag a little bit, because now the W vector and the F centripetal are helping each other, and so the tension has to balance the two of them. Now position 3, we just have the opposite of position 1, where now we have the T vector going this way, a possible F centripetal, because the velocity could be 0 if that's the turnaround point, and we have a weight vector. And so we end up with, and it's customary to do well, you know what, well, never mind. It's customary to draw it this way, but if strictly speaking, it would be better to draw it this way, because now plus W perpendicular, now it's easy to see that the W parallel, which is also going to, remember that, well, again, I don't know what chapter this problem is in, but A equals F over M, so that means that A and F have to be parallel or anti-parallel, because we're multiplying by a scalar, but since M is positive definite, that means that A and F are always in the same direction. Okay, hope this helps.